Okay, in problem 5 we have the Osbornator 9000 roller coaster where it starts at a height h, basically at rest, and then the car plunges down this hill to ground level, and then it goes through a loop of radius r. We want to know how big can this loop be, so what's the radius of this loop, how big can the radius of this loop be without the cars falling off. So what you can imagine, I think, is, I guess I can't do a copy and, no, I guess I can't do that. So, anyway, let me just quickly sketch the thing out. So, okay, and so the radius of this is r, height of this is h, h equals 25 meters, okay, and so we want to know how fast this can be going, or how high how big this circle can be for the cars not to fall off the loop. We're ignoring non-conservative forces, no friction, none of that crap. Okay, so at this point, call this 1 and then say this is 2. Okay, so at point 1, the kinetic energy of the car is 0, of course, and the gravitational potential energy is going to be equal to mass of the car times g times this h, which we've already said we know what it is, but it's going to be mgh. Okay, at point 2, so you can imagine it goes a little bit down, its potential energy goes to 0, so we're saying, we'll say this line here is u equals 0, and at point 2, its kinetic energy equals 1/2 mv squared, so it's got some speed v here, right? And kinetic energy is 1/2 mv squared, and gravitational potential energy is going to be mg times 2 times the radius. Okay, so you know, it's a distance r up from the ground to the center here, and that's another distance r up to get to the top. So ug was mg2r. Okay, so at position 1, e mech equals mgh, and at position 2, e mech equals 1/2 mv squared plus 2 mgr. So we set these two equal. This isn't going to solve everything for us. We get mgh equals 1/2 mv squared plus 2 mgr, and we can cancel out the m's, right? Boom, 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 and we can get you know, gh. I'm going to say, let's see, I'm going to say g times h minus 2r equals 1/2 v squared, or v squared equals 2gh minus 4gr. Let's look at it that way. So that's pretty simple there, right? What this gives us is, depending on this radius r, how much velocity the cars will have. Now the thing is, how much velocity or how much speed do these cars need to have when they get here? Suppose, for example, we had the cars going at a speed of 0 when they got here, so they just barely sort of make it up here, and their speed is 0. Well, they're going to fall. They're going to fall off the track if that happens, right? So how fast? And you can sort of imagine if they came through really, really fast, they'd just go, and they'd never be in any danger of falling off. So the question we want to ask is, how slow can the cars be going? So what I'm going to do is I'm going to say right here, we have this car. It's going at a speed of v. So this is when the car is coming around the top of this loop like that. It's got a speed of v that way. It's moving in a circle with a radius r. Now, what is its centripetal acceleration going to be here? What is the centripetal acceleration going to be to keep going around this loop? Well, let's remember our circular motion thing. Circular motion, any object moving in a circle at a constant speed, you're going to have centripetal acceleration equals v squared over r, right? So that's just our basic centripetal motion equation. So acceleration here is v squared over r. And what is actually, what's going to cause this acceleration? Because remember, you can't just say, well, it's going in a circle, there must be a centripetal force. Centripetal force is just another name for the net force. So what are the forces acting on this object, on this car? Well, one force, of course, is gravity. Okay, so there's our mg. Gravity is acting on it. And then what else is acting on it? The normal force from this from the rails here, right? From the track it's running on. So we draw a little free body diagram. FBD for the car. What we have is we have normal force and we have mg. And if we do a sum of forces in the y direction, sum of forces in the y direction is going to equal, and it's going to be accelerating centripetally, and it's going to be accelerating downwards. So we're going to say it's negative MAC. Okay, so the sum of forces in the y direction is going to be negative N minus mg equals negative MAC. And then we can make everything positive, I guess. We can say MAC equals mg plus n. And let's switch colors and pull this on over here and say what is the centripetal acceleration? We found that, right? So we got mv squared over r is going to equal mg plus this normal force. Now we've got unknowns here. Unfortunately, I've got an unknown normal force, but let's think about what the normal force can be. A normal force, remember Smith's second law, a normal force can only push. You can't pull with a normal force. Normal force has to push, which means this normal force has to be pushing it down, and this number n here has to be greater than 0, okay, or equal to 0, but it cannot be negative. So what lets us have the minimum possible speed, the slowest possible speed for this equation to be satisfied, while this is greater than or equal to 0? Well, let's just let this be equal to 0. Okay, so let's take this and just go that. I'm going to say that's equal to 0, and then we get let's see, mv squared over r equals mg. And if we cancel the m's, okay, so cancel the m's. I'm changing colors again, I know. Then we get v squared over r equals g, which means v squared equals gr. This is an expression that gives us the minimum possible speed we can get through the loop with. If v squared equals gr, then this becomes gr over r, which means this is just g. So this is mg equals mg plus the normal force. So at the speed of v squared equals gr, or v equals square root of gr, however you want to put it, the normal force is 0. Any less than that, and you would need to have a normal force pulling on it to keep it up, which you can't have. So v squared equals gr is our minimum speed, and up here, this is where that comes from, potential energy, right? Or what from energy balance is what we find v squared equals. So v squared equals gr and v squared equals this. So that means we can set those two equal, which means we can say, I'm just going to scroll down a little bit to make some space. So we can say v squared equals gr, so we can say gr equals 2gh minus 4gr. And what we get from that is, first of all, we can cancel the g's out. And what we can get is, well, okay, so fine. 5gr equals 2gh. Cancel the g's, and we get 5r equals 2h. And then we get r equals 2/5 of h. And h, we said before, was 25 meters. That's the height of that first hill. So r equals 10 meters is our biggest possible loop in the roller coaster. That's for a radius of 10 meters. The actual height of the loop would be 20 meters. So, whoops, sorry about that. It's a little too far. Yeah, good enough. So if this hill is 25 meters tall, you can come down. The total loop can be 20 meters tall because that's twice the radius, 10 meters, 10 meters. So it's kind of an interesting fact, and you'll notice in the end, it doesn't depend on what gravity is. So if you're ever building roller coasters on the moon or on Mars or on the surface of a neutron star, whatever, still the same relationship between the height of a hill and the height of the loop that can come afterwards, so long as you've got a frictionless track, which never happens, but maybe in the future sometime.